here. Now we're using normal approximation here to the binomial distribution. Now you're not going to ever be asked to do these types of graphs, right? And it says the following plots show the binomial distribution. When you have n equal to 10, that's the first row over here, okay, n equal to 10, and then you have your p equal to 0.2 here, 0.5 and 0.8. And you can see what happens there. N is staying the same, but the p, the probable chance of getting it, is increasing. So 0.2, 0.5, 0.8. You can see there's less here in the high end because it's a very low chance of getting it. And then when it's 0.5, it should be even, you know, symmetrical. And then when it's high, there should be more on the upper end. Then for n equal to 20, again, 0.2, 0.5 and 0.8. So you have more n's. N is 50 and n is 100. And you sort of see, you can see how the normal distribution always comes in. Okay. Down the bottom, you can see it says when n is small and p is close to 0 or 1. So that one there, the distributions are skewed or symmetrical. If n is large, like we have here, and p is not too close to 0 or 1, so about the middle, it's basically more approximately normal. Okay, so just a bit of information. Oh, I forgot to do that. Now, really, let me clear that because we can't see it. The mean and standard deviation of this normal distribution agrees with those of the binomial distribution. What does that mean? Okay, we have our mean being to NP and our standard deviation being the same as before. Okay, NP, remember I write mine as NPQ. Okay, that's my standard deviation. And remember, variance is always NPQ. Now, what's my Q? My Q is 1 minus P. Remember, I always write that for you guys just to understand it. You can see the textbook doesn't do it. They write the 1 minus P. I want you to get used to both of them just in case you ever see a Q there or the exam puts the Q there and you're not sure what it means for. This is exactly what we've been doing anyway, anything. And here's a little point, both NP and N, and that is Q, must be greater than 5 for satisfactory approximation. So we're going to use that approximation only to do it. So let's do an example. Okay. It says a sample of 1,000 people from a certain city were asked to indicate whether or not they were in favour of the construction of a new freeway. It is known that 30% of people in this city are in favour of the new freeway. Find the approximate probability that between 270 and 330 people in the sample were in favour of the new freeway. Okay, so we've got our sample. There is 1,000 people in our sample. So there's our N, 1,000. It says 30% of them are in favour. 30%, 30 divided by 100. 0.3. That means my 1 minus P, or my Q, must be 0.7 because, of course, it adds up to 1. And they add up to 1 now. So we got my P. Okay. Now, this is what we know. Because we're finding the approximate probability, we can use the two rules above. The mean being NP and the standard deviation. And there we go. We're working this out. So we've got N being 1,000 times my P of 0.3, I've got 300, and my standard deviation. Now I could have just used 300 instead of that, 1,000 times 0.3, but it doesn't matter. Times the 0.7, the square root of that, square root of 210. So we want the probability, and it says here, approximate probability that it is between 270 and 330. Okay, so we're going to now work it out. Because we're using the normal CDF to this binomial, we're going to use normal CDF. We know our 270, there it is. We know our 330, and we worked out our mean, and we worked out our standard deviation. And once we work it out, we get our answer of 0.961566, etc. So we can use that approximation by working out the mean and standard deviation and then using the normal CDF to do these questions. Any questions there?
No.
Okay, that is the last